Welcome back to the series Organic Chemistry for Biohackers. Today we are talking about covalent bonds and what the frick even are covalent bonds. Well, first let me inquire, what the frick even is this? This is omega-3 fatty acid, EPA, super healthy for your brain, super healthy for your whole entire body. It is a polyunsaturated fatty acid. You get it in high quality nuts and seeds and cold water fatty fish like salmon and sardines. And all these lines here are covalent bonds. Also, what the frick is this? This is butyrate. Butyrate is a short chain fatty acid. So if you're taking very good care of your gut, you have a healthy, diverse gut microbiome, you're drinking probiotic rich foods like kombucha, yogurt, kefir, or you're like eating a lot of really healthy prebiotic fibers, then the good bacteria of your gut are gonna ferment those prebiotic fibers into all these really great, healthy postbiotics, short chain fatty acids, anti-inflammatory compounds. And some of those short chain fatty acids that your good gut bacteria are making are things like butyrate. And those lines here all represent covalent bonds. Where we actually left off, we were doing hydrogen bonding in DNA. This whole mess case is supposed to represent the hydrogen bonds in DNA. What's actually happening right here and here and here and here, it's all covalent bonds. When your DNA bases are complementary base pairing, the base guanine and cytosine are bonding by hydrogen bonds. But the actual nitrogenous base itself, like without its partner over here, this nitrogenous base composed of nitrogen, hydrogen, carbon, these are all covalent bonds. Part one, what is a covalent bond? A covalent bond is when two atoms are sharing electrons. And this happens when two atoms are sharing the electrons of their outermost shell, so their valence shell electrons. When those valence shells electrons are being shared, that's a covalent bond. You can have atoms sharing one electron, so there's two electrons making the covalent bond. You can have atoms sharing two electrons, so you have a double bond, or you could have atoms sharing three electrons, and that would be a triple bond. So I'm going to show you what that looks like. First example is going to be carbon. And when you are figuring out what covalent bonds are existing where, you're going to want to have a periodic table with you, and you're going to want to know how many valence electrons a specific atom has. We're going to start with drawing carbon. We're only going to draw we're going to draw the whole entire carbon atom with all of its electrons. And when you're looking for figuring out its valence shell electrons, we go, okay, 1, 2, 3, 4. Because carbon is along the fourth, it's like in the fourth square from here. Because it's in the fourth square, we know it has 4 valence electrons. Oxygen, for example, it's in the 1, 2, 3, 4, 5, 6 little square. It's got 6 valence electrons. Nitrogen, 5 valence electrons. Fluorine, 7 valence electrons. Whatever this is. Neon, 7 plus 1 is 8 valence electrons. Okay, so we're gonna draw carbon's entire electron situation, and then I'll show you the carbon double bond situation. And that carbon-carbon double bond is what you find in your omega-3 EPA fatty acid. This is carbon-carbon double covalent bond. This is a carbon-carbon single bond. This is what you see in butyrate, your super healthy, anti-inflammatory, brain-healthy, short-chain fatty acid. They're all carbon-carbon single bonds. So let's figure out this carbon atom electron carbon double bond situation. First, we're gonna draw carbon and all of its electrons. So this C represents carbon. Here's its first electron shell. It has got 2 electrons in it. When you're going 1, 2, 3, 4, 5, 6, 7, 8, that is referring to their valence shell, their outermost shell. Carbon, 4 electrons in its outermost shell. So here's its outermost shell, and we are drawing its electrons like this. 1, 2, 3, 4. This is just one carbon molecule existing by itself. We're gonna make a carbon-carbon double bond. So let's draw his other carbon buddy here. Here's the innermost shell, 2 electrons. Here's the outermost shell, 4 electrons. The outermost shell, these are your valence electrons. These are the electrons that are gonna be shared. When carbon is doing a carbon-carbon single bond, let's start with the single bond, these electrons are being shared. So you have carbon bonding with carbon, and that is C2. That's it. Not very much exciting things going on. It's literally carbon here, sharing electrons, and this is a C2 molecule. Carbon can also exist in carbon-carbon double bonds, which is what you see in this omega-3 polyunsaturated fatty acid. All these double lines here represent carbon-carbon double bonds. So let's draw the carbon-carbon double bonds here. This is carbon-carbon double bond situation. So we've got carbon-carbon, a double bond represented by 2 lines. Each of these lines, by the way, represents 2 electrons. Literally exactly right here, when you see all of these lines, let's actually just go over this quickly. In organic chemistry, there are carbons literally everywhere. Like everything in organic chemistry, you're dealing with carbon, hydrogen, and oxygen. That's pretty much organic chemistry. Just to make everything easier and more simplified, there's no more you don't draw things like that. That takes so much time. What organic chemists use instead is just straight up lines. This line to this line to this line, and these points represent carbons and hydrogens and the electrons. Every kink represents a carbon. Every line represents a covalent bond. And then where you see this kink carbon, there's actually 2 secret hydrogens here as well, just because these 2 electrons need to be bonded to something for the molecule to be stable. So all of these kinks have hydrogens attached. When you are looking at this long chain fatty acid, for example, every single one of these kinks represents a carbon. Each of these kinks has 2 hydrogens attached. This end kink has 3 hydrogens attached because a carbon follows this thing called the Octet Rule. It will pretty much always be making 4 bonds. In this polyunsaturated fatty acid, this kink here has 2 hydrogens attached, but this kink here has 1 hydrogen attached because this carbon molecule has already got 3 bonds. So this carbon molecule now has 4 bonds. This carbon molecule now has 4 bonds as well. Carbon molecules will always be wanting to make 4 bonds. I think that concludes this part. Here is your carbon-carbon double bond, 2 electrons on the innermost shell, 4 electrons in the valence shell, 1, 2, 3, 4, 1, 2, 3, 4. These 2 carbons are sharing 2 electrons each. So it is a carbon-carbon double bond. Each line represents the sharing of 2 electrons. That is your petite little introduction to covalent bonds. Now we're getting into, let me check my agenda. Also, I always notice at the ends of these videos, my voice gets raspy. And I don't know if it's because I'm breathing in the whiteboard marker fumes or if it's because I'm talking too much. Okay, covalent bonds, electron sharing. Check that off the agenda. Glucose oxidation. Burning sugar. This is glucose. This is your body's primary, most ideal, rapidly burning, available, potent source of energy. Your body really likes to burn glucose and your brain really likes to burn glucose. Your brain likes glucose so much that one of the jobs of cortisol, stress hormone in the stress response, is the glucose sparing effect. Literally what that means is the hormone cortisol is helping fat cells release fatty acids into the blood. So non-CNS, non-central nervous system, non-brain tissues will be encouraged to burn fats. So you save the glucose for your brain. It's all about saving glucose for your brain. Glucose is 4 calories per gram, which literally just means there's X many energy units per gram. So glucose stores a lot of energy. And when we oxidize glucose, we are breaking these carbon-carbon covalent bonds and extracting the energy stored in these bonds and using that to make ATP. ATP is what powers all your body's biochemical reactions, allows hormone synthesis, cell trafficking, signal transduction, DNA repair. ATP is how your body actually uses energy that is coming from burning glucose and burning fats. One very important detail I forgot to mention, covalent bonds are the strongest type of chemical bonds. And they are the strongest type of chemical bonds because they are the sharing of electrons. Hydrogen bonds, which we covered in last video, it's pretty strong, but it's not the strongest because recall that hydrogen bonds are just attractive forces. It's the attractive force between a partial positive and a partial negative, not sharing electrons. Covalent bond, yes, sharing electrons. The key point is covalent bonds, these are your strongest bonds. Fuel molecules like glucose are made up of many covalent bonds. When we are burning glucose, we are breaking these covalent bonds and extracting the high energy electrons and using that to make ATP. Ticking that off the agenda, glucose oxidation and fatty acid oxidation. Just to show you the fats again, fats are worth 9 calories per gram. Look at how many carbon-carbon bonds there are. There's just more opportunity to take out these high energy electrons than there are in glucose, and therefore fatty acids, long-chain fatty acids in particular, have higher energy yields. Fatty acids are 9 calories per gram, 9 energies per gram. Glucose is 4 energies per gram. And that is literally just because in this fatty acid, there are even more carbon-carbon bonds, so just more high energy electrons. Last thingy majigger we're going over, polar covalent bonds. What is a polar covalent bond? A polar covalent bond is a covalent bond, but it's polarized. There is a polarization of charges. The electrons are not equally shared. So in this carbon-carbon molecule, C2, the electrons are equally shared. One carbon molecule is one carbon molecule. These molecules are the exact same thing. They have the exact same electronegativity. When they're sharing electrons, it is the equal sharing of electrons. For example, water is a polar molecule. The covalent bonds in water are polar. Oxygen is not hydrogen. Hydrogen is not oxygen. Oxygen is way more electronegative than hydrogen, and because oxygen has so much electronegativity, it's pulling all the electrons in the covalent bond towards itself. Oxygen has increased electron density. The electrons of that covalent bond are closer to oxygen than they are to hydrogen. And so because of this increased electron density around oxygen, oxygen is accumulating a partial negative charge. Hydrogen is starting to get a partial positive charge. The partial negative on oxygen compared to the partial positive on hydrogen, this makes something called a dipole moment. Literally all it means is that we are dealing with a covalent bond and there's more electrons over here than there are over here. When you have polar covalent bonds, you can now potentially start making hydrogen bonds. See the hydrogen bond video for the millionth time to learn more about that. Last thing we're gonna cover in this video is nothing, because that was everything I had to say about covalent bonds. So I hope you all have a lovely day. And if you want the complete set of notes accompanying the series Organic Chemistry for Biohackers, go to my website, nutritionbyelsa.com, and you can get the complete notes there. I also have a few freebies on my website too. So the video I did on fatty acids, the complete notes, those are free and available on my website, nutritionbyelsa.com. I hope you all have a lovely day and see you later. Bye-bye.